Section 13.2, number 8 on your homework sheets. The pressure in a certain tire is 109 kilopascals. What is the pressure of air in the tire and atmospheres? We know from the data table that 1 atmosphere equals 101.325 kilopascals. We start with the information given, 109 kilopascals. Then we multiply by a fraction. The fraction is equal to 1 because the amount on the top of the fraction and the amount on the bottom of the fraction are equal. We know that kilopascals has to be on the bottom of the fraction so that the units will cancel one another out. We know that atmospheres has to be on the top of the fraction because the question is asking us to give an answer with atmospheres as the unit. So now we have atmospheres as the unit. All we have to do is the math. When we divide 109 kilopascals by 101.325 kilopascals, we get 1.08 atmospheres. This is section 13.2, question number 9 on your homework sheets. The question reads, the air pressure inside a submarine is 0.62 atmospheres. What is the height of a column of mercury balanced by this pressure? According to the data table, 1 atmosphere equals 760 millimeters of mercury. We start with the information that we're given, 0.62 atmospheres. Then we multiply by a fraction that is equal to 1 because the information on the top is equal to the information on the bottom using this equation. 1 atmosphere equals 760 millimeters of mercury. We know that atmospheres goes on the bottom because it has to cancel out the atmospheres that we started with. We're left with the unit millimeters of mercury, which is what the question asked for. So now all we have to do is do the math. When we multiply, we get 470 millimeters of mercury. This is the problem from section 13.2, number 12. The problem reads, a gas container is fitted with a manometer. The level of the mercury is 15 millimeters lower on the open side. Using a laboratory barometer, you find that atmospheric pressure is 750 millimeters of mercury. What is the pressure in atmospheres of the gas in the container? First, we draw a picture. The picture shows the gas in the container, the mercury, and the open end. The mercury is lower on the side that has the open end than on this side. That means the atmospheric pressure is pushing harder than the pressure of the gas in the container. Therefore, the atmospheric pressure must be greater than the pressure of the gas in the chamber. Since we know that the atmospheric pressure is 750 millimeters mercury from the problem, we subtract 15 millimeters because the gas in the chamber is going to have less pressure than the gas outside, or the atmosphere. So we know that the gas in the chamber has a pressure of 735 millimeters of mercury. Now that we've found that there are 735 millimeters of mercury of pressure inside the container of gas, we need to convert that number to atmospheres since the problem asked us for atmospheres. So we're going to multiply that number by a fraction that has 1 atmosphere on the top and 760 millimeters of mercury on the bottom, since those two are equal according to the data table. The millimeters of mercury will cancel one another out, leaving us with atmospheres for the units, and that's what we're looking for. So now we divide. And the answer is 0.967 atmospheres. Section 13.2, problem number 13 on your homework sheets. Imagine you are applying for a summer job in a chemistry lab and you are asked to determine the pressure in atmospheres of an enclosed gas. You find that the level of mercury is 30 millimeters lower on the side of a U-tube attached to the gas container. The barometer shows the atmospheric pressure is 745 millimeters mercury. What do you report? First, you draw a picture showing that the mercury is lower on the side of the container of gas than it is on the side that's open to the atmosphere. The difference is 30 millimeters. This picture tells us that the gas is pressing harder than the atmosphere is pressing. So the pressure of the gas must be greater than the pressure of the atmosphere. Since the pressure inside the container is greater than the atmosphere, we add the difference to the atmospheric pressure. The problem tells us that the atmospheric pressure is 745 millimeters of mercury. We're going to add the difference of 30, and result is 775 millimeters of mercury. Now we take the resulting amount, and we multiply it by a fraction. That's going to bring us to the units of atmospheres that the problem is asking for. We put millimeters of mercury on the bottom so that it will cancel. Then we do the math. The answer is 1.02 atmospheres. This is the problem from section 13.3, problem number 7 on page 4 of your homework sheets. It reads, the guest list for a party in the problem that was already solved has swelled. You suddenly need 350 helium balloons. To buy 350 balloons on the same budget, you can buy only small balloons that hold 2 liters of helium at a pressure of 1.05 atmospheres. If all the other information remains the same, how many balloons can you fill with one tank? According to Boyle's law, the pressure and the volume of the gas inside the tank will be equal to the pressure and the volume of the gas when all of the gas is released into the balloons and the balloons are filled. So the pressure and volume that have 1 subscript represents the tank. Pressure and volume with 2 subscripts represents the balloons. We know the value of pressure in the tank. We're told it is 30 atmospheres of pressure. We know the volume is 25 liters of helium. We know the pressure in the balloons will be 1.05 atmospheres. But we don't know how many balloons we'll be able to fill. So we're looking for volume 2 to find the answer to the problem. We're going to rearrange this equation so that we're solving for the volume in the balloon. We rearrange this equation by dividing both sides by P2. When we divide this side by it, they cancel out and leave volume by itself. This is the resulting equation. Now we'll substitute the variables with numbers. Pressure 1 is 30 atmospheres. Volume 1 is 25 liters. Pressure 2 in the balloons is 1.05 atmospheres. The answer is 714 liters. Now, how does 714 liters relate to a number of balloons? The problem told us that each balloon can hold 2 liters of helium. So we have to find out how many 2-liter balloons are in 714 liters. So I divide the 714 liters by 2 liters. So 357 balloons can be filled with this particular tank of helium. This problem is from section 13.3, number 8, on page 4 of your homework sheets. The question reads, A gas occupies a volume of 458 milliliters at a pressure of 1.01 kilopascals and temperature of 295 Kelvin. When the pressure is changed, the volume becomes 477 milliliters. If there has been no change in temperature, what is the new pressure? First, we have to decide which variables are being changed. Pressure changes, volume changes, but the problem states there is no change in temperature. So the temperature is irrelevant for this problem. This is a problem of pressure and volume. So we start with the equation from Boyle's law. Pressure 1 times volume 1 equals the second pressure times the second volume. The first volume is 458 milliliters with a pressure of 1.01 kilopascals. The problem states that the pressure is changed and the volume becomes 477 milliliters. Thus, we are looking for the second pressure because that's the one that is missing. We rearrange the equation so that the second pressure is being solved for. Then we insert the actual numbers in the place of the variables. Start over. Here we inserted 458 milliliters instead of volume 1, 1.01 kilopascals in place of pressure 1, and on the bottom of the fraction 477 milliliters in place of volume 2. We know that the 2 milliliter units cancel one another out, and we're left with kilopascals, which is what we're looking for. Now we just do the math. The answer is 0.970 kilopascals. This is the problem from section 13.3, number 7 on page 5 of your homework sheets. It reads, a group of students blow air at 5 degrees Celsius into a hot air balloon until it is 80% filled with air. When completely filled, the balloon has a volume of 1,600 meters cubed. To what temperature would they need to heat the air inside in order to fill the balloon? Since this problem is talking about volume and temperature, we will use the equation for Charles's law. Volume 1 divided by temperature 1 equals the resulting volume, or the second volume, divided by the second temperature. We are given the information for the first volume, the first temperature, the second volume, but not the last temperature. Therefore, we need to rearrange the equation to be solving for the second temperature, because that's what we're going to be looking for. First, we cross multiply. Cross multiplying yields this equation. In order to solve for T2 by itself, we need to divide both sides by volume 1. This causes the volume 1s to cancel and leaves us with this equation. Before we can substitute numbers for the variables, we have to do a little bit of figuring. The problem states that the first volume is 80% filled balloon. It also tells us that the balloon is filled completely at 1,600 meters cubed. 80% of 1,600 meters cubed is how full the balloon is at first. Volume 1 equals 1,600 times 0.80, or 80%, and that comes to 1,280 meters cubed. Another problem we have is the temperatures have to be converted to the Kelvin scale. The first temperature is 5 degrees Celsius. We add 273 in order to convert it to kelvins. That gives us 278 kelvins. Now we can put the numbers into the equation. We substitute the second volume for 1600 meters cubed. The first temperature is 278 kelvins. The first volume is 1280 meters cubed. When we do the math, we get 347.5 Kelvin. Subtract 273, and the answer is 74.5 degrees Celsius. This question is from section 13.3, number 8, on page 5 of your homework sheets. The question reads, what will be the volume of a gas sample at 309 Kelvin if its volume at 215 Kelvin is 3.42 liters? Assume that the pressure is constant. Again, we'll use Charles's law equation because the information we're given has to do with temperature and volume. In this problem, the volume and temperature that we start with are actually stated second. And we're solving for the second volume. Therefore, we have to rearrange this equation in order to solve for the second volume. First, we cross multiply and get this equation. Since we're solving for the second volume, we're going to divide both sides by T1 so that the volume 2 is alone. We see that the two T1s cancel each other out. That leaves volume 2 by itself. Now we can substitute the numbers into the equation. We substitute 3.42 liters for volume 1, 309 kelvins for temperature 2, 215 kelvins for temperature 1, and now we just have to do the math. Notice that the two Kelvin units cancel out and we're left with 4.92 liters. Section 13.3, number 8, page 6. The question reads, what is the pressure of a mixture of helium, nitrogen, and oxygen if their partial pressures are 600 millimeters mercury, 150 millimeters mercury, and 102 millimeters mercury? For this problem, we'll use Dalton's law of partial pressures, which states that adding all of the partial pressures of the individual components of the gas will equal the total pressure of the gas. So we add all the pressures together, and the answer is 852 millimeters of mercury. Section 13.3, number 9, on page 6 of your homework sheets, reads, a flask contains a mixture of hydrogen and oxygen. The pressure being exerted by these gases is 785 millimeters of mercury, as determined by a manometer. If the partial pressure of the hydrogen in the mixture is 395 millimeters of mercury, what is the partial pressure of the oxygen? In this question, we know that we're given 785 millimeters of mercury as the total pressure of oxygen and hydrogen mixed together. The pressure of hydrogen is 395. The question asks us to identify the pressure of oxygen. In order to do that, we subtract the pressure of hydrogen from the total pressure, and that will give us the pressure of the oxygen. When we subtract, the answer comes out to 390 millimeters of mercury as the pressure of oxygen. We know that Dalton's law says that the pressures of the individual gases within a mixture of gases will add up to the total pressure. If we add these two numbers together, it comes out to the total pressure, And so, because of that, we know that our answer is correct. Section 3.4, problem number 6 on page 7 of your homework sheets. Reads, if the pressure exerted by a gas at 0 degrees Celsius in a volume of 1/1000th of a liter is 5 atmospheres, how many moles of gas are present? We're given 3 values. The temperature is 0 degrees Celsius. The volume is 1/1000th of a liter. The pressure is 5 atmospheres. We also have our ideal gas equation, which is pressure times volume equals the number of moles times the universal gas constant times the temperature. So the first thing we're going to do is place the numbers that were given into the equation. Before we can do that, though, we have to convert the temperature to absolute temperature in kelvins. We know that in order to change Celsius degrees to kelvins, we add 273. That's pretty easy to add to 0. So the temperature we're given is 273 degrees Kelvin. Now we'll put those values into the equation. Now that we've placed the numbers into their proper spots, P is replaced by 5 atmospheres, V, or volume, is replaced by 1/1000th of a liter, N remains in the equation because N is what we're looking for, the number of moles. R is a constant value, 0.0821 atmosphere liters per mole Kelvin, and the temperature is in kelvins. First thing we can see is that the kelvins cancel one another. We'll start by canceling those out, and then we'll multiply. This side comes out to 5/1000 atmosphere liters. On this side we still have N, and we have 22.4 atmosphere liters per mole. Now, in order to get N in the equation on one side of the equal sign by itself, we have to divide both sides by 22.4. In order to divide a fraction, we multiply by its reciprocal. So we're multiplying both sides by the reciprocal of this particular fraction with moles on the bottom. On this side, both fractions cancel one another out. When we come over here, we see that these two units cancel these units out, and we're left with moles. And now we have to do the math. When we divide 5/1000ths by 22.4, we come up with 223 thousandths. Now we need to change this to scientific notation. We'll move the decimal 1, 2, 3, 4 places. It becomes 2.23 times 10. When we move the decimal place to the right, it's a -4. 1, 2, 3, 4 places. 2.23 times 10 to the -4 moles. Section 13.4, number 7, page 7 of your homework sheets. Reads what volume would be occupied by 100 grams of oxygen gas at a pressure of 1.50 atmospheres and a temperature of 25.0 degrees Celsius. The values we're given are 100 grams of oxygen gas, so we know it's O2, 1.50 atmospheres of pressure, 25 degrees Celsius, and the universal gas constant we already know. Again, we're going to use the ideal gas constant. We know the pressure We're asked to find the volume. We know the ideal gas constant, we know the temperature, we don't know the number of moles, but we have sufficient data to figure out the number of moles. We can use 100 grams of oxygen to figure out how many moles of oxygen there are. 100 grams of oxygen multiplied by 1 mole of oxygen on top, and the molar mass of oxygen as a gas on the bottom, which would be 32 grams, equals 3.125 moles of oxygen. The temperature also has to be changed into absolute temperature in kelvins. By adding 273, we get 298 kelvins. Now we will replace the variables in the formula or the equation to solve for volume. We place 1.50 atmospheres for pressure. Volume remains a variable because that's what we're solving for. 3.13 rounded for the moles of oxygen, the universal gas constant, and the temperature in kelvins. Now we'll cancel out any units. We see that moles and kelvins cancel. Now we'll multiply. When we multiply, we get 76.5. The units are atmosphere liters because that's what's left. Now, in order to get volume by itself, we're going to divide both sides by 1.5 atmospheres. When we divide, these cancel. The atmosphere units cancel. We're left with liters, which is what we're looking for when we look for volume. Now we divide. Our answer comes out to 51 liters of oxygen.